Okay, yeah, welcome back everyone to the ZAG seminar. Today we're very happy to have Georg Oberdieck from the University of Bonn, who will tell us about the holomorphic animal equations for the Hilbert scheme of points on the K3 surface.
Okay, thank you very much for the invitation. It's great to be speaking this long-running seminar. So I will give this talk, and this is about a recent paper of mine. So you can also look on the archive, and it will be some sort of technical talk. And so I apologize for that already from the start, but I try to at least give some sort of background. And I want to start very basic with basically the structure of holomorphic anomaly equation for elliptic curves. Then I will go to how it looks like for K3 surfaces, and then come to this new case of Hilbert schemes of points of K3 surfaces. So in the end, there will be applications. So if you tune out in the middle, then you can come back at the end. So there will be some concrete numbers about hyperkähler varieties, geometry of hyperkähler varieties, some concrete counts that are interesting to study. So yeah, I will highlight that at the end. Okay, so maybe to start, I don't know exactly what is the background, so let me just start from the very beginning. So, so I messed this up here. Okay, so what we study here is the Gromov-Hitten theory, and how is that defined? So let's say you start with an arbitrary X, a smooth projective variety, and then you can consider a certain moduli space here. Which is this conservative moduli space of stable maps. So this is usually denoted MGNX beta. And so this parameterizes pairs. So I forgot the second part here. Parameterizes pairs of a map from a curve. So C here is a nodal curve of genus G, arithmetic genus G. And so you parameterize a pair of a map from this curve C to your target together with n marked points on this curve C. And so the conditions are that the markings should not lie on the singular locus of the curve. The push forward of this class is this class beta that you fix a priori in the cohomology in H2. And then there's a certain stability condition which says that the automorphism group of the curve C that respects the markings and this map F should be finite. Okay. And so the way you should think about this is as, I mean, open locus really parameterizes maps from smooth curves to your target. And then you add some sort of a boundary. You make this compact by adding maps also from nodal curves. So this description is, of course, as a description as a set, but yeah, this really is a modular functor. And as such, it is you can view it really as a proper, it really becomes a proper DM stack yeah, that you can work with. And so moreover, it's what is called virtually smooth. So it has what is called the perfect obstruction theory. So it has a nice theory of deformations and obstructions. And then Li Tian and Baron van Tecke tells us that there's actually a nice class that features as some sort of virtual fundamental, as a sort of fundamental class on the model space, this class here. And it lives in, and it has some unnatural properties. For example, if you integrate it, these numbers that you get out will be invariant under deformations of your space X. So yeah, so in particular, so Gromov-Hitten invariance will just be defined by integrating natural cohomology classes against this virtual class. So the way to do this in practice is you look at their natural evaluation maps on the moduli space. So given such a pair of a map together with mark points, you can send this pair F, and you can send this pair to the evaluation of F at the ith mark point. Okay, so this is this evaluation map. And then you also have psi classes, which are, well, they're called cotangent line classes. Essentially, you have a line bundle, natural line bundle on the moduli space that parameterizes whose fiber at a given point is just the cotangent space to the curve at the given marking. And then psi I is just the first Chern class of that line bundle. Okay. And so then given cohomology classes gamma I on your target on X, so gamma I have cohomology classes on the classes in the cohomology, so elements in the cohomology of X, and Ki are non-negative integers. You can just integrate the pullback of this class gamma I along the evaluation maps times products of this powers of the psi classes against this virtual class. And so this gives a natural set of invariants. And so these numbers are invariant under deforming X of the variety X. So this gives you a natural set of invariants of your space. Okay, so what are holomorphic anom equation? And that's in some sense, well, you can view this in several ways. One way to view this is as a tool to compute this invariance for a special case, namely for Calabi-Yau manifolds. So let's say X is a Calabi-Yau manifold, by which I say kind of very simply, I just mean that C1 of the first Chern class of your X is 0. And so in this case, if you look at this virtual fundamental class that we had in the last page, this the class of this MGN X beta, this lives in a particular dimension of your model space. So it's a pure dimension class. And if X is Calabi-Yau, it turns out that this the dimension or the degree where it lives is independent of the class beta. In particular, this means that if you choose the degrees of your cohomology classes and the KRs correctly, then this chromorphic invariance can be non-zero for all curve classes. In particular, if you form a generating series, you really get an honest power series of invariants of your space X. So actually, I want to say if there are any questions, please interrupt. Okay. So it means that yeah. So in particular, it makes sense to study this series here that I denote FG. So FG of tau K1 of gamma 1 to tau Kn gamma n. And where we form the generating series of this chromorphic invariance. And so a natural question is now, how much information is in this series? So for example, is there an infinite, so there are infinite number that enter the definition of the series? Are all these numbers kind of new informations? Are they kind of independent new information about your target X, or are there some sort of constraints among those coefficients? So it's a little bit like, for example, you take the Euler characteristic of the symmetric products. Should there be some inherent structure in these numbers, or are there just arbitrary new information? And so similar question you can ask here, and somehow physics already answered this expectation. It gave already expectation in this case. And so physics essentially says two things. So string theory, that first of all, there should be a statement about finite generation of the series. So this series should be an element in the finitely generated Q algebra. So instead of just an element in this power series ring, it should be an element in the Q algebra with a finite number of generators. And second, there's a certain holomorphic anom equation that that determines you. So this is a recursive formula for the derivative of the series then as an element in this Q algebra. So you write your FG as an element in this Q algebra in terms of some generators. And then you can formally take the derivative along some of these generators and get a recursion. So that's somewhat way. So let me just explain this in this talk. I will explain several examples of this phenomenon. Okay. And so this is the first question is, where can we look for this? What are Calabi-Yau manifolds we can test this on? And somehow the simplest case is perhaps the elliptic curves. So in dimension 1, you have elliptic curves. You can also have elliptic orbifold P1, so quotients of elliptic curves by a finite group action. Yeah, so essentially these are the two cases you can study in dimension 1. Then in dimension 2, you can study K3 surfaces and abelian surfaces, and you can see structure like this in both cases. And then kind of in dimension 3, the really interesting cases are the Calabi-Yau three-folds, in particular this quantic three-folds. There's been very beautiful work on this the last 3-4 years. So in particular by Zhang Bo and Li and Guo, Yanda and Huan. And then also local surfaces and orbifold Calabi-Yau three-folds and so on. So there's some list of cases that one can study. In dimension bigger than 3, this has not been really looked at. So there was one work by Clem on elliptic Calabi-Yau fourfolds. But otherwise, there's not so much work that has been done. But yeah, so in dimension bigger than 3, what is the structure? So there's this famous Bevil-Bogomolov decomposition theorem that says that if you have a arbitrary compact Calabi-Yau manifolds, then after a finite étale cover, it really it splits as a product of 3 types of varieties. On one hand, there are the strict Calabi-Yau manifolds where the Hodge numbers are 0, except for these 2 extreme cases, H00 and HN0. Then there's the second type, the hyperkähler varieties, and then the third one is the abelian varieties. And so in today's talk, we'll really consider kind of a main example of this hyperkähler varieties, the Hilbert schemes of points of a K3 surface. The strict Calabi-Yau manifolds are in higher dimension well, I think are also interesting, but maybe I will not discuss this right now. The abelian varieties are less interesting just because they're, at least you don't expect to have any curves in dimension bigger or equal to 4 unless they're in some sense degenerate. Okay, so so that will be the plan for today. So start with elliptic curves, go to K3 surfaces, and then go to hyperkähler varieties, the Hilbert schemes of points. And so yeah, so this builds on, I mean, this in dimension less than 3, there's a lot of work of various people. I think I cannot go through the list of all of them, so let me just leave it like this. Okay, so for elliptic curves, how's the story for elliptic curves? And here it's essentially as simple as it can be. Okay, so the finitely generated ring that will play a role here for the chromospheric invariants is the algebra of quasimodular forms. And so I'm giving a definition for this later in the context of quasi-Jacobi forms. So let me just give this definition here just as a, in terms of generator somehow formally as Q series. And so the way this definition works is you look at what I call this classical Eisenstein series. So you look at GK of Q, which is, so the constant term is minus the BK. So BK is this Bernoulli number divided by some factor. And then you have this this number. So the coefficient of Q to the n is, you look at the divisors of n and you weight them by d to the k minus 1. And so, yeah, so this makes sense for even k bigger than 1, and then G2, G4, G6 already generate you the algebra of quasimodular forms. And this is your ring. And then there's a really beautiful theorem of Ukunkov-Pandey that tells you that these chromospheric invariants are always in this algebra of quasi-modular forms of a given weight. Okay, so in particular, this means that on the left-hand side, you really have a power series. So as I said before, we index our classes by beta classes in H2 of X. So if X is the elliptic curve, H2 of the elliptic curve is just Z. And so if you then form this generating series here in the middle, then you just sum over Q to the n, where n is an integer. Okay, so it's just a power series. And so then this theorem tells you that this power series lives in this ring. And that's a very nice theorem because on the left-hand side, as I said, you have infinitely many numbers somehow that enter here. But then you identify it with some p, so some degree k p's in this algebra, which is in fact finite dimensional. And so in particular, you just need to compute finally many numbers to really determine this whole series on the left-hand side. And so this is very nice, but in some sense, it's not often not good enough, particularly in application. It's this space here grows very large. So just to make this as a remark, so this is a remark about quasimodular forms. The question is, how many coefficients do you need to know to actually determine a quasimodular form? And essentially, what a bound that you know is that if you know less than, if you are given a quasimodular form of weight k, then you need to know approximately quadratically many coefficients of your quasimodular form until you actually can determine this quasimodular form. On the other hand, if you modular form, so modular form is an element in the string that does not depend on this G2, then your situation is much better. Then in fact, so this algebra of quasimodular form is just generated by G4 and G6. And then it's kind of a classical statement that the number of coefficients you need to know of a modular form is just exactly given by the dimension of this corresponding vector space. And so in particular, you just need to know the number of coefficients, where this number just depends linearly on this weight k. So it's a much stronger constraint on the function. And so in particular, what you can then show is you can ask, are this FG modular? That's not true, but what you can then this holomorphic anomic equation tells you is the dependence of your series FG on this parameter G2, on this non-modular parameter, and this quasi-modular parameter G2. And so I've written down this equation, and that equation yeah, is a little bit complicated. The way to think about this is on the left-hand side, you have this the series you started with. On the right-hand side, you have series which are easier in the sense of they depend on, so there's a certain grading you can put on the insertions that you put on the genus and this insertion that you have here. And then with this grading, is the series on the right are lower in the grading that you have. So in some sense, this equation is a recursive formula for the derivative of this FG with respect to this G2. Okay. So in particular, for example, the first term is if you take the derivative of FG, then the first term is the function in one genus lower in FG minus 1, where you have the same insertion as before, but then have two trivial markings, tau 0 of 1 and tau 0, two copies of the trivial insertions here. The second factor is very similarly. So so in the first factor is in some sense you create a node in your curve. The second factor is you break your curve into two components, C1 and C2 of genus G1 and G2. And again, kind of the edge term that you enter here is this tau 0 of 1 on both sides. And finally, the last term is the following. So in some sense, you sum over the, here you really touch the insertions that you put in. So you sum over the number of points. You integrate the gamma I. So if you have a point among the insertions, you integrate that point out and instead replace it with a 1. And to keep the same cohomological degree, what you do is you add one more psi class here, so you raise this ki to ki plus 1. And so all the holomorphic anomic equations have essentially a similar structure. And what's really entering here is this term here. Yes.
What is E? The integral over E?
Oh, that's the elliptic curve. So, sorry, so here X is elliptic curve E.
I see.
Yeah, thank you for the question.
Mm.
E will always be elliptic curve in this talk. So in some sense, what goes into this equation really is this term here, this tau 0 of 1, this edge term that you have to specify. Once you specify the edge term, then you essentially can write down this equation easily. And also this term here at the bottom here, integrating the point and then replacing it with a 1 is essentially just applying this edge term to the class of to a class on the elliptic curve as a correspondence. Okay, so are there any questions? Okay, so this in some sense classical stuff. There's various proofs of this, and also in fact various proofs of this earlier theorem now. There's this classical proof using Gromov-Witten-Hurwitz correspondence. There's this proof using this double ramification cycle, and so on. So this is kind of a well understood path. So let me come to K3 surfaces. Okay, so this is kind of the next case, and this is already more interesting, and also there's a lot of new phenomena that appear. So So smooth projective K3 surface is a K3 surface if it's symplectically connected, and there exists a holomorphic symplectic form on this K3 surface, on this surface. And so then now there's in some sense a subtlety that appears here. So the symplectic form tells you that not all classes in H2 on your surface are in fact coming from algebraic curves. Only some of them are really algebraic classes or even Hodge classes. And the way to think about this is to be algebraic just means that you should be orthogonal to the class of the symplectic form in the cohomology lattice H2. And so in particular, if the sigma varies in moduli, so if the sigma, so there's a moduli space of K3 surfaces, which is essentially given by the period domain. So if you move in this period domain, this just corresponds to moving the sigma. And then the orthogonal to the sigma also changes or jumps under this move. So in particular, it really matters which K3 surface you take in what are the curve classes. And so to formulate this correctly, in some sense, the neatest way is just to work with elliptic K3 surface from the start, and then this one calculation by a deformation argument will determine you the invariance in all different cases. So so the way this works is, so all K3 surfaces are deformation equivalent to an elliptic K3 surface pi. So as you have elliptic fibration S to P1 with a section. And then we can look at the class of the section, we call that B, and then we can look at F, which is the class of the fiber. Using these two classes, then we can form a generating series, again, of our invariance. So we have FGM. And so here we have two parameter, G is the genus as before, and M will denote the degree of your curve class over the base of your fibration over your P1. So we have this bracket and we sum over the curve classes. So we fix this degree MB, and then we sum over all the D's here. And in some sense, that's in some sense arbitrary. Well, not arbitrary, how do you say? A special case. In some sense, you want to generate over all of it. But for now, this is the place where you can really identify modularity in this homomorphic invariance of this K3 surface. So eventually we will just sum over all M, but at this point, I think it's the most convenient way to formulate this thing. And so here's a second small thing that I didn't explain. So instead of tau K1 of gamma 1 to tau Kn gamma n, we'll just weight our integrals by class alpha, which is just a tautological class on the model space of curves. So this is completely analogous to the previous definition. I mean, the set of numbers here are equivalent to the set of numbers I defined earlier. This is just a more convenient way to formulate this. And so finally, for the experts, we have the symplectic form. So really, we need to work with this reduced virtual fundamental class. So that's a small technical aside. And so now, essentially, the same story as before just should go through perfectly. So the conjecture here, and that is a old conjecture by Maulik, Van der Pand, and Thomas, says that this that the series FGM that of the K3 surface are always in the algebra of quasimodular forms. So here quasimodular form with respect to a certain congruent subgroup, this gamma 0 of M. Okay. So I'm not going to explain this. Maybe later I say a few words about this. Together with a certain prefactor 1 over delta of Q, which is delta of Q is here the natural discriminant modular form. Okay. And so maybe to make the story short, so again, this gives you a finite generation statement for this series. And then as before, you have a certain splitting. So the algebra of quasimodular form again has G2 of Q in it as a free generator. So it is just a polynomial ring, polynomial algebra in G2 over the algebra of modular forms. And then as before, you can say what is the dependence of this series on the G2. So, so this is the following conjecture. So this was first actually proven for m equals to 1 by in work of myself with Aaron Pixon, and then later on Boehm-Buell proposed this generalization for higher m. And so here, yeah, so here's this recursive formula, and maybe I say a few words about the structure of this equation. Okay, so if you go back 3 slides to the elliptic one, so let me go back to the elliptic equation. So in the elliptic equation, we had 3 terms here: fg1, fg minus 1, the splitting term into 2 curves, and then the last term where the psi class gets increased. And so in the K3 surface, we have exactly the same 3 terms. So it's on the right hand side, we have the first term, which is the fg minus 1, that decreases the genus by 1. Then we have a second term where the genus is split into two summands. And then we have the third term where we have an additional psi class entering here in this at the I factor, where you apply some correspondence or some map to the ith cohomology class. So there are 2 new factors here in this definition, and so essentially 2 new things. The first thing is the last term, and I will comment on that in a second. And then the second thing is that the edge term here is different. So you have to choose a different edge term. And the way this goes is you have to, instead of put 1, 1, there's a natural choice that you have to, that appears here very natural, is to insert the diagonal of the base P1. So S maps to the P1. And then if you take fiberwise the 1, 1, that's just the pullback of the diagonal downstairs. Okay. So the edge term here is provided by this delta of P1. And finally, there's this correction term at the end. So let me just explain this notation. So if you have a lattice, for example, H2 of S, or the cohomology lattice, and you have if you take wedge 2, an element in second wedge in this lattice, for example, V wedge W, then it acts naturally on this lattice just by this formula down here at the bottom, applying W to X, and then minus applying V to pairing W with X, and then minus pairing V with X. So that is essentially wedge 2 of a lattice is naturally isomorphic to the Lie algebra SO of that lattice, and then this isomorphism is really provided by this map. And so here the definition is as follows. So if you have V wedge W and apply this to the series, we just say that we apply this or we sum it where we apply this to this ith factor. And so essentially this is the natural way to if you have a Lie algebra acting on a vector space, then there's a natural induced action on the nth tensor product of this vector space just by essentially this formula that you have here, namely you apply to just apply to the ith factor and then sum over all I. And so here the EA where you do this, so you apply this Lie algebra action twice to this insertion gamma 1 to gamma n, and you do this by this wedges here where the EA runs over the basis of the orthogonal to this span of B and F in this H2. So it's some technical formula that you have here, but it's kind of working perfectly and has then been used to prove various things about K3 surfaces, K3 times elliptic curve, and so on. So again, this basically, reduces the determination of the series FGM from a quadratic bound to a linear bound of coefficients that you need to understand. So what is known in this case? So the finite generation statement is known for m equals to 1, and then so this means m equals to 1 is degree 1 over the base, and the advantage here is that then all the curve classes that you look at, so mb plus df, are all primitive. So this is essentially the case of primitive curve classes. Here, this was proven then by Maulik, Pandan, and Thomas, this finite generation, and then this holomorphic autonomic equation was proven in my work with Aaron. And so then essentially there's this work of Boehm-Buell, and essentially what's the idea is to the key essentially to proving something for m bigger than 1 is using what is called the multiple cover rule. And so here the idea is the following. So essentially there's the observation that the series FGL, or FGM, so that we had before, this FGM, all determined by the series FG1 by a kind of a simple rule. And the way this is formulated is here at the bottom. So there's a conjecture with Bande that if you look at the, okay, so now it's switch M to L. So if you look at the L series or the M series, it is determined by the series where you have degree 1 over the base from the application of a certain Hacker operator to this series. So you have a certain formal Hacker operator on power series that basically reshuffles you the coefficient a little bit and with some factors, and essentially from this applying this to this series in degree 1 gives you the arbitrary series. And then essentially the nice observation of being Bull is that if you assume this multiple cover conjecture and then finite generation in holomorphic anomic equation for m equals to 1 implies it for also for higher m, for arbitrary m. And so after showing this, then they show that essentially this multiple cover conjecture is true in m equals to 2, and then they conclude this theorem. So really there's really 3 statements here that are kind of crucial for the K3 surface: finite generation, holomorphic anomic equation, in this multiple cover conjecture. Okay, so I will continue now to the Hilbert scheme case, the new stuff. I don't know if there are any questions. Maybe I go back one. Okay, so let me say a few words. So now I will come basically to the main part of this talk, the Hilbert scheme case. And so that's, I think, an extremely beautiful geometry. So we start with S, the K3 surface. And then there's Sn, which is a Hilbert scheme of n points on this K3 surface. So Sn is just, as I said, it parameterizes subschemes, closed subschemes of S, which are 0-dimensional and have length n. So in particular, if you look at the support of your 0-dimensional subscheme and you view it with multiplicity, then it will just consist of n unordered point. So there's a natural map from the Hilbert scheme of points to the symmetric product. And this turns out to be a resolution of singularity. So in particular, a wonderful thing about the Hilbert scheme is that it's in fact a smooth variety. So this is so one way to think about this Hilbert scheme is really to think about this in the Grothendieck way of definition as a Hilbert scheme of subschemes of a given space. But what's really beautiful in this case is there's a second way to think about this as namely as a hyperkähler variety, as irreducible hyperkähler variety. So this is a result of Beville that says essentially that this Sn has the properties of a K3 surface, but viewed but in higher dimensions. So in particular, it is simply connected. And then the second condition is that the space of its holomorphic 2 forms is just generated by a single form sigma, which is again a symplectic form. Meaning that it's non-degenerate, so it's nth wedge. It gives you a trivialization of this canonical band. And so in some sense, this Hilbert scheme of points has a dual role, somehow dual nature. One is a Hilbert scheme, which kind of yields a lot of tools. I mean, there's work of Götze and Nakajima and Goranowski and Lehn, Manfred Lehn, and a lot of people about Hilbert schemes of points on surface that you can apply. On the other hand, it's also part of this hyperkähler world and from there you get a lot of tools, for example, this global Torelli theorem, deformation theory, and so on. And so in some sense, combining these two things will essentially allow us to basically kill or to determine a lot about the Gromov-Hitten invariance of this space. And so essentially the short upshot of this talk here is that once you interpret it suitably and you set it up correctly, then you have exactly the same structures as for the K3 surface. And we have multiple cover conjecture, finite generation, and holomorphic anomic equation. And the upshot of this I will explain a proof of for certain cases of this conjecture, and they will lead really powerful ways to actually compute stuff. Okay, so okay, I apologize for this technical stuff. I mean, it's just part of this theory. So so in some sense, I have to explain this same thing as before for K3 surface. Have to explain for the Hilbert scheme. And so again, we'll do the same thing. We'll move to an elliptic K3 surface with section. So S will be again elliptic K3 surface with a section. And then if you move to the Hilbert scheme, you have a natural vibration that is induced by this map when it's a Lagrangian vibration. And essentially it's defined by if you are giving me a subscheme of length n of your K3 surface, I can look at its underlying support, that's n unordered point on that K3 surface. I can apply this vibration map and land with n unordered points on the P1. So get n unordered point on the P1, and then the symmetric product of P1 is just isomorphic, is naturally isomorphic to the nth projective space Pn. So this gives a natural vibration, and the fiber over the point corresponding to n distinct points will just be the product of the corresponding fiber elliptic curves which lie in the fibers of this n points. So it's really the generic fiber is really I mean it's a smooth Abelian variety, and then it fits kind of nicely together to give a Lagrangian vibration. And so we'll do the same thing as before, summing over curve classes which are of a fixed degree over this Pn, and then sum essentially over all the curves which are over all the fiber classes. What's new here, a new feature is here, in fact, that there's an additional class that appears. So if you look at H2 of your Hilbert scheme, it is isomorphic to H2 of your underlying K3 surface plus Z times the new curve class where A, which I call A, and which is the class of the what is called the exceptional P1. So if you look at subschemes which are supported at n-1 points, so where one of the points has multiplicity 2, then that loci is naturally isomorphic to a P1, and the class of that one, that loci, we will denote by A. So in particular, if you do the story that I did before, you have to deal with this extra class. And so in particular, if you define now this generating series, you have to keep track of you have to insert a new variable that I call P here, that appears here naturally. So with some of the curve classes, L times the class of the base, there's a certain shift that I will not explain here. And then essentially with some of this D and the R, which is the fiber class, and then this A class. And again, we have a tautological weight. And so so the series is what we have to discuss, and where we have to state finite generation in holomorphic economic equation. And so instead of working quasi-modular form, the way this will turn out, we have to, so because we have an extra variable, quasi-modular forms will not be the answer, but instead the answer will be given by quasi-Jacobi forms. So let me explain this in a very quick way, or in a slide here. And maybe I will explain this a little bit, because I think this is, I've never seen this explained in a geometry talk. And in the modern forms talk, you never explain the geometry. So maybe I explain this here. What is a Jacobi form? And in fact, a quasi-Jacobi form in a very quick way. So the idea is instead of viewing the series we had before, so we had the variables P and Q. Instead of viewing them as series in P of Q, you make this variable change to Q. You view as e to the 2 by I tau, where tau is in the upper half plane. And then this variable P you view as e to the 2 by x, where x is in the is your elliptic parameter, x is in C. And so then there's this classical notion of Jacobi forms. This was introduced by Eichler and Serge, and essentially the definition is that a Jacobi form of weight k and the given index m are holomorphic functions on the upper half planes times C. So you insert x and x in tau. That satisfies two transformation laws, essentially transformation law with respect to the Jacobi form, which is a semi-direct product of SL2Z and two copies of Z. Okay, and essentially that essentially two transformations. The first one, maybe the second one is easier to understand. Is so if x is the element in C, it tells you if you have this function, you evaluate it at x, and you evaluate it at x plus a lattice point of your elliptic curve, then it tells you the ratio of these two values is given just by the exponential of a certain factor here. So E of something stands for x of 2 pi I of that something. And the second, if the first one is really, in some sense, the crucial thing, it's what happens if you change your elliptic moduli tau by SL2 transformation. And so this is some Jacobi forms. There's also a final condition about being holomorphic at infinity that I ignore here. And so what are quasi-Jacobi forms? Quasi-Jacobi forms are holomorphic parts of almost holomorphic Jacobi forms. So the way this looks like is you look at functions here, which are finite sums. So this should be finite, given by Fij times variable alpha I in nu to the nu. And the alpha and nu are non-holomorphic variables. In fact, they're given down here. So nu is just given by constant times one of the imaginary part of tau. And then this alpha is given by imaginary part of x divided by imaginary part of tau. So on the left-hand side here stands really a non-holomorphic object. But we ask this non-holomorphic object to satisfy the same equation as before. And so a quasi-Jacobi form is something which is F00 of an almost holomorphic Jacobi form of this form. So in fact, sending an almost holomorphic Jacobi form to its constant term, in fact, you can reverse that process. You can kind of recreate the series on the left-hand side from this F00 term. And so in fact, this gives you isomorphism. So in some sense, quasi-Jacobi forms you can view as holomorphic functions that satisfy this transformation law up to some correction term, or you can view them as non-holomorphic objects which satisfy them on the nose. And so then you can form an algebra of quasi-Jacobi form, where again the weight spaces, where you have weight k in index m, these are finite dimensional spaces. And moreover, you have two free generators corresponding to these two non-holomorphic parameters, nu and alpha. So you have this G2 of Q, you have this A of PQ. So this is the algebra we will work with, and then you can exactly formulate similar conjectures as I had before for the case of the Hilbert scheme. And so the first conjecture, so this was beginning of last year, I put up this paper, essentially says that you have this analog of this multiple cover conjecture. So there's a certain formal Hecker pair of Jacobi forms that you can write down, and you can actually find in Eichler-Zagier. And if you apply this to the FG1, it should be exactly this FGL. So here L is the degree of the base Pn. So this first conjecture essentially says that in studying this counts of Gromov invariants on the Hilbert scheme, you can reduce from imprimitive curve classes to primitive curve classes. And then there's the second conjecture, which says that this FGL here is the element in this algebra of quasi-Jacobi form for a certain congruent subgroup. And then again, you have a certain prefactor here. And then finally, and that's kind of the most important part, is again, you can write down a holomorphic or normal equation. And again, the surprising thing is, well, we have two of them. We have one for G2 and one for A. The A one is less interesting, but the G2 one is in some sense the main thing. And in some sense, the intrinsic, the nice thing is that it exactly has a similar form or similar features like the one for K3 surfaces. So again, we have four terms. And in some sense, the only thing we need to understand is what are the edge terms here, and what do we do in this last term. And so the answer in hindsight is kind of obvious, but back then, really the key tool to use the key tool that appeared here is something from hyperkähler geometry. This is this Lojenga-Lunz-Verbitsky algebra. So let me explain this in this one slide here. So what is this algebra? So this is an algebra that you can attach to any smooth projective variety, but which is particularly useful for hyperkähler varieties. So let me just explain this. So if you have X a hyperkähler variety, you can look at the Lie subalgebra of the Lie algebra of endomorphisms of your cohomology, which is generated by all left sets as a two triples EA, H, and FA for all A where these where such a triple exists. So, for example, if A is an ample class, then by hard left sets, you know that EA, which is the operator. So if you look at EA, which is the operator of cup product with A, and you look at H, which is the left sets grading operator, so it acts on H to I by I minus the dimension of your space, then given these two operators, if A is ample, then there exists a third operator, which is FA, which is the left sets dual operator. And essentially, then for this is the existence of this FA is an open condition among this A. So in fact, you get kind of a whole bunch of this SL2 triples, and you just throw them all into your Lie algebra. And so then there's a very useful fact by Verbitsky that this Lie algebra that you get out of is in some sense as small as it can be. It's just wedge 2 of H2 of your hypergala variety. So that's a Bevil-Bogomolov lattice. Yeah. So it's a lattice with respect to this Bevil-Bogomolov-Fujiki form plus a copy of this hyperbolic lattice. And so then for the Hilbert scheme of points, if you run this thing, you get really decomposition in this H2 of this K3 surface plus the trivial summit. And so the upshot of this is that there's a natural representation, this LIV representation, and then you can define kind of this natural operators, get natural operators on cohomology out of this, which is just using this structure that we have here. So the key edge term here in this definition is this U, which is just looking at F, which is the fiber class of your elliptic vibration, wedge little f, which is an element in this hyperbolic lattice. And so then you just insert this into this thing, and you are happy. So also this last term is essentially the same. You just have to apply this LLV representation. And so then, in some sense, this first theorem about quasi-Jacobi form, I knew basically already a while ago. This is essentially outcome of my PhD thesis. So there it was conjectured in a very basic case, but in some sense, the general thing was always clear to me. This holomorphic annoying equation, it's really more recent. And what's even more recent is to actually be able to prove something about the structure. And so the theorem is that if you look at genome 0 and up to 3 markings, so up to 3 cohomology insertions, then all these 3 conjectures hold for, in fact, for all Hilbert schemes of points. So an arbitrary dimension, you have a complete proof of this structure, at least in this genus 0 case. And so here I should also say that in some sense, what is the virtual dimension of this model space? It's something like 2n minus 3 times 1 minus g plus 1. So in fact, in higher dimension for n bigger or equal to 3, there you only have genus 0 and genus 1. So in really genus 0 is the interesting case. And so there are 2 corollaries that you can get. One of them is that this reduced quantum cohomology of this Hilbert scheme is determined up to finitely many coefficients for each n. And then a second one is something about this generating series of 2-point invariants that it defines your vector value Jacobi form of weight minus 10 in index n. Sorry, this is missing down here. Basically taking values in the cohomology of the Hilbert scheme tensor itself. Okay, so I don't know how much time I have, maybe 12 minutes, is that correct? So okay, so maybe I spend 5 of this 12 minutes to explain a little bit what goes into the proof of this theorem, and then I give 5 minutes for application and actually given some concrete numbers. So with respect to the proof, essentially there are several, so in some sense there's a lot of formality that we set up, a lot of formulas. But once you set this up correctly, then there are some natural reduction steps that kind of go through very naturally. And one of them is that you can use this multiple cover conjecture to reduce really to this case of FG1. So once you have that multiple cover conjecture, you can prove that finite generation and holomorphic normal equation for FG1 implies the same thing for FGL. And so there's an argument how to prove multiple cover conjecture in this case that I can, if somebody asks, I can explain. But in some sense, the crux then is to just work out this case for FG1. And there are essentially two tools here that we will use, 2 or 3, but in some sense, 2 main tools. The first one is to use the monodromy of these hyperkähler varieties to get really relations on this FG1. And so to explain this, if you have the Hilbert scheme of points on the K3 surface, you can deform, of course, the K3 surface, but this will not produce any new relations. But instead, you can view this as a hyperkähler variety and apply this global Torelli theorem. And then in this model space of hyperkähler varieties, this locus of Hilbert schemes of points of a K3 surface is just a divisor. So you can deform out of that loci and deform to a space which is no longer the Hilbert scheme. And so if you do this and apply monodromy using this operation, then you get relations which are not clear from this Hilbert scheme structure. And so in particular, there's 2 that one can use here, which are crucial. The first one is is the first one that I wrote here is, so W here should be B plus F. So I'm sorry for that. So the first one is acting on H2 or H lower 2 as follows. So it sends this curve class B plus F plus DF plus RA to a certain linear combination. And so then the observation, it's a simple observation, is if you look back to the definition of quasi-Jacobi forms here, and in fact, exactly in the second line here, in the second transformation law, then you see that this factor here on the right, you have this lambda square, and this lambda is exactly matches you this deformation property of this monodromy here. So that's kind of the key observation in this business, that somehow half of the structure of this Jacobi forms you already see using this monodromy. What is then a little bit harder and what is more kind of more tricky? So this, of course, it's because of this global Torelli theorem, it's easy to say what a monodromy does in H upper 2 or H lower 2. Then you have to say what does it do on the whole cohomology lattice, and this is exactly where the place where this LLV algebra, this Loyenga-Lunz algebra, comes in. I mean, it tells you precisely how this monodromy acts on the whole cohomology lattice. And so, in fact, you get this the action on the cohomology classes then is exactly given by this e to the lambda of certain operator in this LLV algebra. So this requires a certain understanding of I mean, this is in some sense a crucial link between hyperkähler geometry and this Jacobi forms. And so there's a second one where you place RA by minus RA and you get a certain sign. So that gives you one half, and then the other half, so I wrote here, this deformation can be viewed as deforming K3 non-commutatively. Yeah. The second half is work of Nesterov. So this is about a certain warp crossing statement using quasi-maps, which relates invariance of the Hilbert scheme, Komov invariance of the Hilbert schemes to Donaldson-Thomas or Pandey-Thomas, so sheaf counting invariance of the product of this K3 surface with the curves C. So in this case, P1. And so in particular, to how this works is if you look at this certain generating series of Komov invariance of the Hilbert scheme, where you sum over this exceptional curve class with a certain variable, then essentially the statement is that this series is exactly equal to a certain series of Pandey-Thomas invariance of the surface times P1. So on the left-hand side, you have genus 0 and 3 markings. This corresponds to surface times P1, and then relative to 3 fibers over this P1. That's in some sense the first step, and that's a kind of complicated step and geometrically challenging. And then there's a third key step you're not done, that you have to prove a certain correspondence between Pandey-Thomas and Komov invariance that allows you to go from PT to Komov invariance of the surface times P1. And so there's work of this by Pandey and Pixon, but it's not quite enough because there's a certain vanishing cohomology on K3 surfaces under degeneration. So you have to extend their method and then prove a certain correspondence here between PT and Komov. And so once you're here in this chain, then there's a nice tool in Gromov-Itten theory. You have a product formula. So in fact, using a product formula, you can just go back. You can reduce to the Gromov-Itten theory essentially of a K3 surface. And so this means that you can use this old results of MPT and myself with Aaron on this holomorphic anomic equation of K3 and trace this back through this line of correspondences to what it says on the Hilbert scheme. And in some sense, and that's kind of fortunate, it just works out to be exactly the other half that you need to establish this modularity for this Hilbert scheme of points of K3 surfaces. And so in some sense, combining this then exactly proves you this FG, I mean, this final generation holomorphic anomic equation for this FG1. And multiple cover conjecture again is kind of a completely it kind of uses also this wall crossing, but it yeah, from there it uses certain technical arguments in Pandit-Thomas. Okay, so I have 5 minutes left, so let me just give some examples and applications and actually produce some numbers here. Maybe basic example here. So how is it useful to have this theorem? Let me give one example. So let's say you take elliptic K3 surface and you look at the induced Lagrangian fibration. If you take two fibers of this Lagrangian fibration, you can ask what's the series of Gromov-Itten invariants. Essentially, when I wrote my PhD thesis, this was the first one I looked at and studied and computed. And it took me really half my PhD thesis to compute this, to prove this. So how does it work here now? So essentially, it's now completely easy. So you first have to understand. So by this first theorem, you know it lives in some certain space of quasi-Jacobi forms. And by a certain very easy computation, you can compute the weight and the index of this Jacobi forms. And in fact, then this it's easy to see this space of quasi-Jacobi forms is just a one-dimensional space spanned by a certain power of a theta function here. And then finally, you just need to fix a single coefficient to tell you what is the constant in front of this Jacobi form. And so here, essentially, you can look at the class of a line in this Lagrangian P2 that has a certain class, and then you can just compute the Gromov-Itten invariance in this case. A line through 2 points, and Pn is just there's just a unique line, so the certain invariance is 1, and you get this result. And so by similar arguments, you can essentially compute all Gromov-Itten invariants in genus 0, 1, and 2 for the Hilbert schemes of 2 points of a K3 surface. And I counted it as essentially just need 7 elementary computation as I done in this last slide. Maybe a little bit more complicated, but something you can just do directly without problem. And so this was then done, worked out in joint work with Yalong Chao and Yukinobu Toda, where we also defined Gupa-Kuma-Wafa invariants of the Hilbert schemes of 2 points, which are invariants which are conjecturally integer and should kind of reflect more closely the innovative geometry of curves in this Hilbert scheme. So Gromov-Itten invariants are rational numbers whose innovative meaning is often not clear, and then this Gupa-Kuma-Wafa invariants should produce the integers underlying this counts should really count you something. And so, for example, in genus 2, you have you expect your moduli space to be 0-dimensional, so you don't have any deformations. So you just get a single series here, which is computed assuming this holomorphic anomic equation. And then from this, you can compute the Gupa-Kuma-Wafa invariants and produce you, for example, the list of genus 2 Gupa-Kuma-Wafa invariants of hyperkähler fourfolds of this K3 two-type. And so this should be the expected number of genus 2 curves in this geometry. And yeah, so I can say a few words about this if somebody asks later on. In some sense, the very interesting thing is this first number where it's non-zero, and there's something that we even don't understand geometrically. So 11.5 is precisely this case of de Bas-Voisin fourfolds. And this computation suggests there should be 3,465 isolated smooth genus 2 curves of minimal degrees, so degree 11 in this de Bas-Voisin fourfold. So it would be very interesting to check this computation here using this geometry. And then finally, there's some application to Galileo threefolds, Donaldson-Thomas theory of Galileo threefolds, but maybe I skipped this. I think everybody is probably tired already by this formula. So I just show you these numbers from the time, and then I thank for the attention.
Great. Yeah. Thanks a lot, Georg, for this nice talk. Are there any questions from the audience?
Can you say some more on Calabi threefold?
This last slide, you mean?
Yeah.
Yeah, I mean, I'm saying that you can use this as a machine to compute Donaldson-Thomas invariance of Calabi threefolds. In particular, this what is called the CHL Calabi threefolds. So if you start with the symplectic evolution or any symplectic automorphism of a K3 surface of finite order, then you can associate a certain Calabi threefold to it, which is K3 surface times elliptic curve, where you quotient out this product action of this given symplectic automorphism on the K3 surface times the shift by a torsion point on the elliptic curve. So in this case, G is an involution, and then tau is shift by a 2 torsion point. This produces you a non-strict Calabi threefold, and then you can look at its series of Donaldson-Thomas invariants. And one of the outcomes of this machine here that I discussed here is that you can then use this to prove that this generating series of Donaldson-Thomas invariants is really a Jacobi form. You can then later probably also use this to determine this. I haven't thought about this, but I think I'm optimistic about using this to actually compute this.
Thank you.
Is there a similar application to these Borsea-Voisin Calabi-Yaos?
Yeah, not yet. I mean, I don't think, not directly. I mean, you need probably some new ideas. But yeah, that would be very interesting.
Other questions from the audience? I mean, I guess you did mention this multiple cover conjecture implying, finite generation for FGL for L high. I mean, could you say a few words about this argument? Or?
Yeah, so so in some sense, again, you use this theorem of Dennis Nesterov that brings you back to Pandey-Thomas theory of the surface times P1, or even you can go to Donaldson-Thomas theory of surface times P1. And then from there, you can essentially reduce to K3 surface times P1, where you don't have any relative divisors, or let's say only one relative divisor. And then you can apply localization on the P1. And then that produces it goes you down to some sort of nested model space of sheaves on your K3 surface. And then you can study the deformation obstruction, the obstruction spaces of this nesting. In some sense, you can show that each nesting produces you a trivial summand in the obstruction sheaf. And by this reduced class, essentially you can one of the summands is always taken care of, so one of them is always taken out. But if there are more than one, then you get a vanishing of the corresponding virtual class of the fixed loci. So this gives you a lot of vanishing after localizing on this P1, and then essentially using this together with some sort of universality of integrals of over model space of stable pairs on K3 surfaces, then lets you conclude this statement. So this, I mean, this is part. I mean, the original ideas were from the work of Pandey and Thomas, where they proved this Katzkin-Barfer conjecture for K3 surface, and then essentially you have to extend this to this more general case here, surface times P1. But yeah, that's in some sense a second argument, which in some sense uses this reduced class. This is essentially the reason why we have kind of this nice structure, this nice multiple cover conjecture.
Are there other questions from the audience? Doesn't seem like that's the case. In that case, thanks a lot again for this talk. So yeah, I'll stop the recording. Where's the button?